Yeah, good morning my dear students. Today I am going to discuss the topic on electrothermal atomizer, particularly how graphite furnace can be used in atomic absorption spectrometer as an atomizer. This graphite furnace is basically used in most of the modern atomic absorption spectrometers. We are going to discuss about the construction and the working of graphite furnace. So this is the construction of the graphite furnace where the light radiations are passing in here, and there is an exit over here where the light radiations are going out. Light radiation in the sense particularly the hollow cathode lamp, the light radiations are, that is the source for your atomic absorption spectrometer. From there the light radiations are getting inside the graphite furnace, and here in the center we are having the sample port for injection. Okay, you will be injecting the sample in the center port, and there will be a curved LO platform will be there, and here this is the furnace wall, right, and the light outside will be going here, right. So this is the way light in and this is the way going for light out, right. So this is the general arrangement of any graphite furnace, right. So what is an advantage of using this furnace? In the last class we discussed about the flame atomizer, nebulizer burner system. What is the greatest advantage of using this furnace over the flame atomizer? The first important advantage, it provides a great sensitivity. The second important thing, it is having a less sample for analysis. Even you are getting very less sample, particularly in microliter, 1 to 100 microliter, this lesser sample also can be analyzed with the help of your graphite furnace. Okay, this is a major aspect. Now, what is the description of this graphite furnace? Sample injected in the center, it will be going through this 38 millimeter long tube. There is a long tube here. This long tube is particularly the diameter of the tube is around 38 millimeter. Now, atomized sample in the path, that atomized sample, the sample gets atomized here, right, with the help of the graphite furnace. The purpose of any atomizer to make the sample to make the sample atom in the gas phase ground state. That is the purpose of any atomizer. So, in order to bring the atoms into the gas phase ground state, this particular platform or this particular sample, it will take several seconds. It is this atomized sample path will take several seconds, and therefore it increases the sensitivity. Whereas in case of your flame atomizer, it will not take much time, but here it takes several seconds. This is an advantage. So sensitivity will be better. And with the help of this graphite furnace, we can also use nanoliter volumes also. When we talk about the nanoliter volumes, one of the classical example is renal tubular fluid. So if you want to analyze the concentration of sodium and potassium, we can even go for dragging 0.1 nanoliter from the person, that is from the renal tubular fluid, and then we can go for analyze with atomic absorption spectrometer using graphite furnace. Then automated sample injection increases the reproducibility, obviously. Injecting the sample, the droplet, particularly if you inject the sample here, particularly the droplet, when the droplet will contact the floor of the surface. The floor of the surface will be the droplets, whatever is formed, it will contact the floor of the surface, right. So this is all about the description. And the methodology, when we discuss about the graphite furnace methodology, the temperature programming is done with several minutes. What are all the steps we are performing for our sample? We have to adjust the temperature or pre-programming the temperature in the furnace previously before subjecting the sample, right. So it depends upon the sample to sample. For example, if you are using iron as a sample, right, if you want to measure the concentration of iron in iron storage protein ferritin, so what are all the conditions we have to apply? So generally there are 4 important conditions. One is called drying, charring, and then atomizing and cleaning. These are the 4 important steps normally, right. Drying will be there, then charring will be there, atomizing and cleaning. But before every step of these things, we have to do one important step called purging, right. So if you look at the methodology here, the first step is purging. Why we have to purge? Purge it with inert gases like argon or nitrogen or some gases, right, neon and all. We are purging with some inert gas inside the graphite furnace initially for some time period. What is the role of purging? To prevent the oxidation of graphite, an argon gas is possible. We have to purge it with argon gas, right, to prevent because it is a graphite furnace, it is coated with graphite. So in order to prevent the oxidation of graphite, we have to just purge the entire furnace by passing the argon gas, particularly for some time period. What is the time period we are using? 2550 degrees centigrade for not more than 7 seconds. And remember that this is the protocol only for measuring the concentration of iron in ferritin, not for all the samples. Okay, for different samples the temperature will be different. Now the second step is drying. That is a very important step. Why we are doing drying? The sample will be dried to remove the solvent, because the solvent will interfere. So therefore you have to remove the solvent from the sample. So we have to go for drying, because you have to get the pure atom sample in the gas phase ground state. Okay, so we don't want any liquids, solid liquids and all, particularly solvents we don't want, right? To remove the solvent, you have to go for drying. The temperature used here is 125 degrees centigrade for 20 seconds. Now the third important step, again purging we have to do, but this time we are not doing the purging for particularly to prevent the oxidation. This time we perform the purging by passing the argon gas to remove any volatile material present in the graphite furnace. Okay, so to remove the volatile material, we are again doing the purging. So this time the temperature will be the same, 2550 degrees centigrade for lesser than 7 seconds, right? After purging, then the very important step is charring or pyrolysis. What is called charring? That is nothing but the decomposition with heat. That is called charring or pyrolysis. So this charring, what is the purpose of charring? To destroy the organic matter, we have to use the charring step, and particularly at a temperature of 1400 degrees centigrade for 60 seconds, 1 minute, right? Why we do the charring? And this charring, when you perform, it contains the smoke that will interfere with the determination of the ion sample. So charring step, whenever we perform, it will definitely produce a smoke, and they will interfere with the final determination or the concentration of the element ion, right? But it is an unavoidable step, right? So atomizing, what is the next step? The next step is atomizing. Atomizing is the very important step, you know very well. To make the atoms in the gas phase ground state, we are using the step of atomizing. The main purpose of your atomizer is atomizing. So which is the major step? The vaporization of the sample takes place at a temperature of 2100 degrees centigrade for hardly 10 seconds. And when we do this atomizing, the absorbance reaches the maximum. You will get the maximum absorbance. You will get a very sharp signal like this, right? You will be getting a very sharp signal like this, because we are using the atoms, right? So for every element, we will be getting a very sharp signal in the atomizing step. Then after atomizing, again we have to do the purging step in order to remove the volatile material by passing argon or nitrogen gas at the same specified temperature what we have discussed previously. And the last step is cleaning. Sometimes we are not doing purging after atomizing. We can directly go for cleaning also, depending upon the sample what we are using. So cleaning, to clean out any remaining residue. So the temperature for cleaning is 2500 degrees centigrade for 3 seconds only. Okay. So these are all the various steps we are using, especially in the graphite furnace, right? Now coming to the furnace performance, how the furnace will be giving the good operation mechanism. If you look at the sample heated by radiation from the furnace well, sample vaporizes when the furnace wall reaches the constant temperature, right? So whenever we go for the sample heated by radiation from the furnace wall, right? And then the sample vaporizes when the furnace wall reaches the constant temperature. So the temperature inside the furnace should be very, very constant. Then only the sample will undergo the vaporization. Okay, so area under the absorbance peak at a constant temperature, the area under the absorbance peak is a reliable measure of total analyte vaporized from the sample, right? So this is the way you should remember that. And for example, if the heating rate of 2000 Kelvin per second, if you are keeping, so they will quickly dissociate the molecules and increases the concentration of free atom in the furnace. How will you get the free atom in the furnace in the gas phase? Only by using the high temperature, say 2000 Kelvin per second, right? There are two types of furnaces we are using. One is called transverse type, another one is called longitudinal type. In transverse type, that is from side to side, whereas longitudinal type, it is from end to end, right? So what is this advantage and disadvantage? Particularly in the longitudinal type, the atoms in the central region will condense at the ends. Suppose if the atoms in the central region, they will just condense at the ends, because this type of thing is here, right? So what will happen? The atoms from the central region will try to condense at the ends. Okay. When they are condensing at the ends, what will happen? Where they can vaporize during the next sample run. Because the next sample is also coming there. Because when you want to find out the concentration of several elements using atomic absorption spectrometry, first I want to determine iron, second I have to determine lead, third I have to determine copper or bismuth. If I go for metal concentration to determine in this sequential manner, so what will happen? In longitudinal surface or longitudinal type of graphite furnace, they can vaporize during the when the central region will be condensing at the ends, where the next sample by the time when they come in, so they will interfere with the previous run. So this is an unwanted phenomena. This will interfere from one element with another element concentrations, and therefore this effect is called as a memory effect. Is it clear? Where they can vaporize during the next sample run, the interference from previous run is called memory effect, right? So how to rectify this memory effect? You can go for using the transverse type graphite furnace, because they are the best one as compared with the longitudinal type of graphite furnace. And the second important rectification also we can do that, even if you use the longitudinal type of graphite furnace, try to use, instead of using the ordinary graphite, you try to use the pyrolytic graphite, which is having a dense layer of carbon, right? So they will try to seal the porous graphite as such, right? So we are making the use of pyrolytic graphite in case of your longitudinal graphite furnace, whereas in transverse furnace will be the better one if you are using directly. This is the rectification method for avoiding the memory effect, right? Now, when we add the sample, I told here we are using the sample. Sample will be dissolved in solvent. Sample plus solvent we are using. We are using sample plus we are using solvent, right? Plus we are using matrix modifier. There is another thing called matrix modifier. Okay. Not only sample and solvent we are using, we are also using matrix modifier. What is the purpose of this matrix modifier? Everything present in the sample will constitute the matrix. Okay, other than the sample, whatever is present, everything is called as matrix, right? So what will happen? And this matrix, it is decomposed and vaporized during the charring step. When you do the charring step, right, or pyrolysis step, this matrix will be decomposed and they will also get vaporized, right? So what is called matrix modifier? That means this is an interference. Matrix is an interference. Your sample will be there, along with the sample some other substances are present, they will cause the interference, right? So those substances are called matrix and they will cause matrix interference. To avoid the matrix interference, we are just adding the matrix modifier. What is a matrix modifier? It is a substance added to the sample to decrease the loss of the sample during the charring step. The main purpose is the substance, if you want to determine the concentration of iron, the iron should not get decomposed during the charring step. This is the purpose, right? It should not get lost. So that is the purpose of any matrix modifier. And the mechanism how the matrix modifier acts, there may be two possible mechanisms. Either the matrix modifier substance, when we are adding, what will happen? The matrix will be getting more volatile. If you add the matrix modifier, they make the matrix more volatile, or they make the sample less volatile. Both the things are possible. Either the purpose of matrix modifier, they make the matrix more volatile, or they make the sample less volatile. Both of them are possible, right? So I am just going to give some example here. The first case, we are adding the ammonium nitrate, right? I want to determine the concentration of manganese ion in seawater. Okay, if I want to determine the concentration of manganese ion in seawater contains, you know very well, sodium chloride, right? So I want to specifically find out the concentration of manganese so that sodium and chloride should not cause any interference with manganese, right? So I am adding the matrix modifier ammonium nitrate. If I add the ammonium nitrate, it will interact with the sodium chloride. So what will happen? Sodium chloride and ammonium nitrate, if I add, so they will form ammonium chloride and sodium nitrate. So sodium nitrate will be just quickly volatilizing when we apply the temperature, and they will evaporate instead of making the smoke. Is it clear? So this is the purpose, right? So ammonium nitrate is added to seawater to reduce the interference of sodium chloride for analysis of manganese in seawater. When we use this sodium nitrate is more volatile substance. So automatically, as compared with sodium chloride, it is more and more volatile. Sodium chloride will not much volatile, right? But sodium nitrate will be more volatile after reacting with the matrix modifier, right? So therefore what will happen? Before the sample gets volatilized, they will just go for volatilization fastly. So therefore they will not interfere with your sample analyte ion. So this is how we are using the matrix modifier, right? There is another example for matrix modifier where we are using magnesium nitrate. If I use the magnesium nitrate, suppose I want to determine the concentration of aluminum in the aluminum sample, I am just adding magnesium nitrate as a matrix modifier. So magnesium nitrate will be at a high temperature, the magnesium nitrate will be converted into magnesium oxide solid, and this magnesium oxide solid will be evaporated and vaporized, so that what will happen? You will get magnesium oxide gas. So magnesium oxide gas, what they will do? This gaseous form of magnesium oxide, they will interact with the aluminum, and they will be converting into magnesium and aluminum oxide. So this is the purpose of magnesium oxide, right? So what will happen? You simply say that aluminum tends to evaporate very fastly, right? So what we have to do that as long as magnesium oxide is present in the sample, right? So what will happen? They will prevent the evaporation of aluminum in a fast manner. Is it clear? So the retardation of aluminum is taking place. That means the evaporation of aluminum is retarded as long as the magnesium oxide is present in the sample. That is why we are using the magnesium nitrate as a matrix modifier. So magnesium nitrate will be converted into magnesium oxide in the gaseous form, and this magnesium oxide will try to protect the aluminum by combined with aluminum and converted into aluminum oxide, right? So therefore it will prevent the more volatility, or it make the sample less volatile. Otherwise the sample will gone away, right? So it makes the sample aluminum less volatile, so that we are using magnesium nitrate as a matrix modifier. So this is all about the various purpose of using matrix modifier in atomic absorption spectrometry. I hope you understand in a better manner. Thank you, my dear students. Thank you very much.